if you look at these two terms, omega p1 over omega p2 plus omega p2 over omega p1, they are interchangeable. So, it does not matter which one is at the lower frequency, that will become the dominant pole. So, that is why you have a symmetry here. So, this becomes zeta equal to 1 over, we had twice of square root 1 plus a naught beta, that will become 2 plus 2. Okay, and what is A beta usually? Is much larger than 1. So, for this case, what will happen to zeta? Zeta will tends to 0. What does it mean? Where are the poles if zeta is 0? J omega axis. Okay. So, you will get a perfect sinusoid oscillations, because your impulse response will become sin omega n t in that case. Okay. So, unstable. And we already saw that even if you keep your second pole at UGB, and UGB is basically A times of your first pole, which means gain times of your. So, you get 45 degrees phase margin, which means if you move the second pole at the omega p1 or first pole, so both poles are inside your UGB, and we know that system will become unstable, and that is what happening here. Okay. Let us take the case 2. So, omega p1 is much less than omega p2. So, what would happen to this? Omega p1 is, so this term will go away. And omega p2 is over omega p1 is much larger than 2. So, now assume omega p2 is at UGB for 45 degrees phase margin. Okay. So, where will be this? In terms of omega p1, 1 plus a naught beta times, correct. So, I am still, I mean, you can ignore 1 if you want, but that is the case if you assume a naught beta is much larger than 1, then you can ignore 1. So, your zeta will become 1 over 2 square root. So, omega p2 is at UGB, and your UGB is nothing but 1 plus a naught beta, omega p1 will cancel out. Okay. So, this will go away. Okay. So, your zeta is half, which is 0.5. So, zeta equal to 0.5. So, now if I have to draw this, let us take one more case. So, for 60 degree phase margin, Can you tell me the relationship between omega p1 and omega p2? Case 3. For so what is phase margin? Is 180 degree. For second order system at UGB, the what will be the phase contribution from first pole? 90 minus. So your phase margin will be mostly determined by second pole, omega over, correct. So 60 degree, which means tan inverse omega over omega p2 equal to 30 degrees. And what is omega? Omega is nothing but omega UGB. So omega UGB equal to tan 30. How much is tan 30? 1 by root 3. Okay. Which means omega p2 is now from here you can find the ratio omega p2 over omega p1. So omega p1 is omega UGB over 1 plus A naught beta. So what is zeta? Can you tell me from here? Zeta is 1 over 2 square root 1 plus A naught beta. Just substitute the values. Square root 3 into 1 plus A naught beta. So what is this? Can you tell me zeta, value of zeta? Hmm? 0.6. This was square root 3. 0.65 roughly. Okay. So now, can you roughly tell me? So for phase margin of 45 degree, I am getting zeta 0.5. And for phase margin of 60 degree I am getting zeta 0.65. So can I say I am roughly between like 90 to 100 times of your zeta is my phase margin. Okay. And this estimate is true when you are looking at more than 45 degrees phase margin or so, up to 90 degree. Okay. Below that it because it has a non-linear relationship, but since our interest is mostly between 45 to 60 degree, so most of the time it will hold true. Okay. So phase margin is approximately 90 zeta to 100 zeta. Now if I have to draw in the S plane, see both poles are at same location and real. What is the zeta here? Zeta equal to 1. What is the zeta here? J omega we just saw 0. What is the zeta here? -1. Huh? It's the same but flip side. Now, if zeta is more than 1, what would happen? The pole will split and one will start moving towards origin, other towards infinity side. Okay. So this is the case for zeta and if you have a zeta equal to infinity, then the pole will come at origin. Okay. In between, so what does it mean? Omega zeta equal to 1 is I mean roughly can I say what is the phase margin there? Okay. So, if you have a greater than or equal to 90 degree, then your pole will be on real axis and you won't have any oscillations, because in order to have the oscillations your pole should be on j omega, basically your pole should be complex, otherwise you won't get sinusoid term. And we know zeta 0.5 was somewhere here. Okay. And second pole will be here. So, omega p1, omega p2. So, what I want, I basically, in order to have a good stable system, I want my zeta to be more than 0.5. Okay, or phase margin more than 45 degrees. So, in this region your phase margin is greater than 45 degree, in this region your 45 degree, and this is considered stable, and this is usually below 45, even though it is stable, I already mentioned, we do not consider is stable, it is a marginally stable. So, usually we do not design any system with less than 45 degrees phase margin. So, here you will have a perfect oscillations. What would happen in this region? You will have oscillations, but they will die out exponentially. Okay. And if you are here, then you will have oscillations, but they will build up exponentially. On real axis, they will just exponentially rise. Okay. Left half plane, real axis, it will rise and settle. Okay. So, that is the relationship between your closed loop and system and loop gain response, where we relate zeta. Zeta is defined by a closed loop system and phase margin is defined by open loop system. But since we can analyze open loop system in a better way perspective, because it is simpler, so we always use the loop gain analysis to find the phase margin and see whether the system is stable or not, and then based on that we decide whether it needs to be compensated or not. Okay. So, usually we when we analyze up to second order system. The reason is that holds true for higher order system also, because we know that any higher more than, if you have a more than one pole in the system, so all the poles should be outside UGB, and most of the time your if you have a more than two poles or it is a higher than second order system, usually the higher order poles are much higher frequency, and when you compensate it, they will hardly affect your phase margin. Your phase margin will be mostly determined by the second dominant pole, until unless your second and third pole are lying on the same frequency, which is very rare case actually. So, now we know how your system looks like in a closed loop and open loop, and now if we are given an unstable system, we need to stabilize it, and we will see how you stabilize, what are the different techniques. Okay. Basically, we will look at compensation techniques. Okay. So, now let us take the case of your LDO. Or linear regulator. So, what is the first thing we need to do to analyze the stability of the system? Using loop gain analysis, we have to break the loop. Okay. And for a small signal, we make it 0. So, your input is applied here, and you observe the output at the other side. So, step 1. So, how to loop gain analysis. So, step 1, break the loop. Okay. Then step 2, we need to find the poles. Find poles and zeros. If there are any zeros, we need to consider those as well. So, I will just copy this. So, what is inside AS? So, I am just drawing, it could be second 2 stage also, I am just drawing single stage just to simplify. If you do not understand this, then you will be taught all these things in analog circuits course, So, this is your V in plus, this is your V in plus, this is your V in minus, this is V out. You have a tail current here. Okay. So, this is nothing but a single stage differential amplifier, where it amplifies the difference between the input and produces the output. So, your V out will be gain times what is V in. So, what is the gain? GM into R out. Okay. And GM is the transistor of transconductance of these two, and R out is the equivalent resistance looking at the output, which is your. So, you have a two resistance here. So, any transistor, this PMOS can be represented as a voltage controlled current source and a resistor. Okay. So, this is your R out, and this is defined as GM multiplied by VGS, which is the gate to source voltage of your transistor. And the same thing for NMOS also. So, the GM comes from this VCCS, and R out is the equivalent resistance looking into the drain of the transistor. Okay. So, now these transistors have parasitic capacitors associated with them. Okay. And these, there could be 3 different caps. So, you have the caps, let me change the color. So, one cap is, so if this is your source terminal, this is your drain, this is your gate, second cap is this, and third cap is between gate to bulk, and this is your bulk. So, you call it CGD, CGS and CGB. And if you know the structure of the and what is the capacitor? Formula for capacitor? Epsilon A over T, thickness. Okay. So, which means if you have a larger area, you will get a larger cap, smaller area will give you smaller cap, and thickness is defined by the process. So, between those the thickness of the dielectric. So, your MOSFET is like this. So, this is your substrate, since this is a PMOS. So, which is fabricated inside N well. Then you have a P plus diffusion, which forms a source. Then you have another P plus diffusion, which is your drain, and then you have oxide here with polysilicon layer, which forms the gate. Okay. So, you have a oxide in between your substrate and gate terminal, and that forms the cap. So, if you look at the between gate to source or gate to drain, it's only overlap. So, the area is very small. So, that capacitor is negligible. The most of the capacitor is coming from gate to bulk. This is your bulk terminal. CGB is and whenever you are looking a capacitor at the gate, the other two capacitor will be automatically added there, okay, because if you look at the common terminal for the 3 caps is the gate. So, where is the maximum cap out of these 3 terminals? Is at the gate. Since G or gate is the common terminal to all the 3 capacitors, we get maximum capacitance at gate. Okay. So, if you have to find the pole, we are mostly interested in lower frequency poles, not a very high frequency poles. So, we know that whenever you have the gate terminal and any resistance, high resistance associated with this, the capacitance will be maximum there. So, these 2 gates are tight. So, you will have a 1 cap here. Okay. And the capacitor at the output is quite negligible. Okay. And when we have a second stage PMOS, then this output cap will become more dominant, okay, because you have a very high value resistance. So, this is mostly considered as a first order system, because the moment you have the PMOS connected at the output of your differential amplifier, that becomes the dominant pole, and this first pole which is coming due to this cap, this becomes negligible. The reason is, if you look at the impedance looking here, our out is much smaller because it's a 1 by GM. Okay. So, mostly we will have a 2 pole system here when we connect the capacitor at the output. So, the first pole will come at the gate, second pole will come at the output, and we will analyze as a second order system, and we will see what capacitor values you require to compensate it. Okay.